In this segment, I'm going to discuss the membrane potential. Let's start off with this hypothetical situation. Here I have a beaker containing two separate solutions, sodium chloride and potassium chloride, with a membrane separating them. This membrane is impermeable to any of these ions. At this point, it's not important what the concentrations of these ions are, just that there's just sodium chloride on this side, just potassium chloride on this side. Let's not worry about the concentrations. Since there's no movement of ions, then we have no voltage across the membrane. What I'm showing here is my reference electrode and the signal electrode, and there's no voltage. Now I'm going to put in a channel. This channel is permeable to potassium only. Chloride cannot move through it, nor can sodium. Only potassium can move. Since potassium is in high concentrations on this side and there's none on this side, potassium will tend to move through this channel. This is causing a buildup of positive ions on this side over here, and a loss of positive ions on this side. There are more chloride now than potassium, so there's a negative charge building on this side. These excess charges then line up along the membrane. Excess positive charges on this side, excess negative charges on this side. Now we see we have a negative 80 millivolt difference between here and here. This side is 80 millivolts below our reference. Well, this number is also arbitrary because it's going to depend on the potassium concentrations, as I will mention in a second. Potassium is going to be moved according to two separate forces. One is the chemical force, the concentration gradient. Since potassium is high on the inside and low on the outside, potassium will tend to move out of the cell. However, there's also an electrical force. Since there's a positive charge building up on this side of the cell, it's going to repel positive charges, and potassium is going to tend to move inward. When these two forces are equal and opposite, potassium movement ceases, and we would say that the membrane is at rest. We have reached equilibrium. Well, there are a couple of rules that must be followed. If we're going to generate a membrane potential, two ions of equal charge cannot be exchanged. That is, you cannot exchange a sodium ion for a potassium ion. No net change in voltage would be perceived. Also, you cannot transport an anion with a cation. So sodium chloride cannot move in or out of a cell in order to change its membrane potential. Another point to remember is that if a positive ion moves into the cell becomes more positive. That's the same thing as saying less negative or depolarized. If a positive ion leaves the cell becomes less positive, which is the same as more negative or hyperpolarized. And you can use the same logic for negative ions moving in or out. Here are the common ions involved in generating this membrane potential. The primary anion inside the cell are proteins. The primary anion outside the cell is chloride. We have open potassium channels, so potassium is free to leave the cell, bringing the inside less positive or more negative, and the outside more positive. Potassium is then pumped back into the cell in exchange for sodium, and that keeps this continually moving. Sodium can enter the cell either with a nutrient such as sodium glucose cotransporter. It can move in through this sodium-potassium 2-chloride cotransporter. It can be exchanged for hydrogen ions, or it can be exchanged for calcium ions. Calcium, on the other hand, must be pumped out in exchange for hydrogen ions. These are the primary ions that are involved in generating this membrane potential. The next thing to talk about is the Nernst equation. And the Nernst equation says that the potential equals minus 2.3 times some constant R, which is our universal gas constant, times temperature in degrees Kelvin, divided by Z, which is the valence or outer shell electrons, and F is Faraday's constant, times the log of the concentration of the substance we're looking at on the inside divided by the concentration on the outside. So here we have the key for these. The Z, which is the valence, is going to be plus 2 for calcium. Calcium has 2 positive charges in its outer shell. Sodium is plus 1, chloride is minus 1. This will determine the charge of the voltage. We can reduce that by taking all these constants, assume the temperature is constant or relatively constant. These two are constant. So for sodium, Z will also be constant. The important point here are these concentrations. Concentration inside over the outside. if the concentration of a substance on the inside is higher than the concentration on the outside, then the log of that number is going to be positive. If the concentration on the outside is greater than the concentration on the inside, the log of this number will be negative. And this will determine the equilibrium potential along with this negative and Z. So for example, sodium. Sodium has a +1 here. So this number is -60. Sodium has a higher concentration on the outside than the inside. Therefore, the log of that number is going to be negative. 2 negatives gives us a positive. Our equilibrium potential is going to be positive. And the opposite could be said for potassium. Another important concept is the Goldman equation. And this looks an awful lot like the Nernst equation up to this point. But now we're adding permeability. P is permeability for potassium on the inside, the outside, for sodium on the inside and the outside, and for chloride, since it's negative, we reverse the concentrations outside over inside. And I'm going to ignore chloride because it pretty much follows the membrane potential. So if we just look at potassium and sodium, and we assume that the permeability for sodium is 0, then the membrane potential will be the equilibrium potential for potassium, regardless of the permeability, will be the equilibrium potential for potassium. If, on the other hand, potassium permeability is 0, then our membrane potential is going to be the equilibrium potential for sodium. However, since the permeabilities for potassium and the permeabilities for sodium are never 0, then the membrane potential is going to be somewhere between the equilibrium potential for potassium and equilibrium potential for sodium. Since there are many, many more potassium channels open than sodium channels, potassium will have a greater tendency to move out than sodium to be moving in. So the membrane potential then, because of the high permeability for potassium, is going to be closer to the equilibrium potential for potassium than to sodium. Now I'm going to go back and discuss a little bit of physics and electronics. You've all had physics courses, so you'll have to dig back into your brain and try to remember these things. A capacitor has the capacity for storing electrons on one plate and pushing them off the other plate. So we have a negative and a positive plate. Between the capacitor, we have something called a dielectric. This dielectric cannot allow current to flow from the negative to the positive electrode, or the capacitor is useless. At the same time, the dielectric must have a dipole. Otherwise, if this were totally nonpolar, the influence of the electrons on this side would have very little effect on the electrons on this side. But because there's a dipole in here, the negative charge building up on this side pulls on the positive end of the dipole, swinging the negative end of the dipole up to this end, which then pushes electrons off. The rate at which a capacitor charges or discharges depends on the resistance and the capacitance. R times C equals tau, which is the time constant. One time constant represents 63% of maximum charge, or we could say 63% of the maximum discharge of a capacitor. What I have here is a capacitor that's all charged up, and I'm going to discharge it through a resistor. By closing this switch, electrons from this side are free to run through the resistor and accumulate on this side until there's no difference in the potential. So at this point, the capacitor is discharged. The rate at which it discharges is then R times C. What we can see here is, at this point, maximum voltage is 100%. We lose 63% of that charge in one time constant, so we're down at 36%. And then one more time constant, another 63%, brings us down to 13.5% of the charge, another 63%, 5. So by 4 or 5 time constant, we would say this is clearly discharged. So why am I talking about this? We can assume that a cell membrane is a capacitor. It has the capability, the capacity, for building up negative charge on this side and a positive charge on this side. The membrane itself then becomes the capacitor. Membrane resistance is determined by the number of open channels. If we're talking about sodium, if we have only one sodium channel open, that's a very high resistance. If there are thousands of sodium channels open, then the resistance clearly is getting smaller and smaller. There's also resistance on the outside of a cell, longitudinal resistance, which is very low on the outside of the cell. On the inside of the cell, there's also longitudinal resistance, and that's going to depend on the diameter of the cell. Very small diameter cells are going to have high resistance. That is, the flow of electricity along the cell membrane is going to be retarded in very narrow diameter neurons and much, much faster in large diameter neurons. So the rate of change of this membrane potential is going to be determined by the number of open sodium channels. So this membrane is going to depolarize based on the number of channels open. In this model, I'm using the Goldman equation to solve membrane potential given internal and external concentrations of sodium and potassium, and also the permeabilities of sodium and potassium. I've set the potassium permeability to 1, and these are arbitrary units. It's unimportant as to the actual permeability, but rather the ratio between sodium and potassium. So I've opened a few sodium channels. So in this example, the membrane potential is at minus 80 millivolts, close to the equilibrium potential for potassium. So if we make this individual, for example, seriously hyperkalemic, we now have raised the potential to almost minus 69. If we now make this individual hypernatremic, the voltage hasn't changed by very much. Changes in sodium concentration have a very small effect on membrane potential, and that's because permeability is so low here. So go back to 140, and we're back to minus 80. Now I'm going to try to simulate an action potential. In an action potential, what happens is that several sodium channels open. So I'm going to increase this sodium permeability by a factor of 100. So I'm going up to 2.5, and we run. The membrane has depolarized to a positive 17 millivolts. Now the sodium channels go back to normal, and potassium channels will open during repolarization. So I'm going to now run this and see what happens. We've dropped to almost minus 85 millivolts. So this membrane is hyperpolarized because of the open potassium channels. And we now come back to normal, and eventually the hyperpolarized membrane comes back to resting. That concludes this discussion on membrane permeability and its effect on membrane potential.